Welcome to the states of gases. So it's useful to picture a gas as a collection of molecules or atoms in constant random motion like this, with average speeds that increase as the temperature increases. And so you can see here we've got lots of different atoms or molecules bouncing around. And if we follow any particular one, it's got this random motion here. Now, it's not just changing direction willy-nilly, it's only changing direction when it collides with another molecule. Now, a gas differs from a liquid in that molecules of a gas are widely separated from one another, and they move in paths that are largely unaffected by the intermolecular forces except for those brief collisions. Now, the physical state of a substance is the set of its physical properties. For example, the state of a pure gas is specified by its volume V, amount of substance, this is the number of moles, N, pressure P, and temperature T. Each substance is described by an equation of state, which is an equation that interrelates pressure, temperature, volume, and number of moles. And so we can say P is a function of temperature, volume, and number of moles. And this equation means that if we know the temperature, volume, and number of moles, then the pressure has some fixed value. Now, note that each substance has a different equation of state, where that for an ideal gas, and note that Atkins calls this a perfect gas, is P equals nRT over V. So let's define a few terms. The pressure, which we're going to symbolize P, in this case a lowercase p, is the force F divided by the area A to which that force is applied. So P equals F over A. And this means that the greater the force, the greater the pressure. Or if we keep the force constant and decrease the area to which that force is applied, then the pressure goes up. So that force applied to the area for a gas is arising from those collisions of gas molecules with the wall. That's the area that we're concerned with here. Now, the collisions of gas molecules in a normal sample of gas are so numerous that the force is essentially constant over time, and thus the pressure is essentially constant over time. Now, the force is measured in newtons, which we symbolize with a capital N, and the area is measured in square meters, or meters squared. And remember that the SI unit of pressure is the Pascal, symbolized capital P, lowercase a, which is then defined as 1 Pascal is equal to 1 Newton per square meter. Now the standard pressure, P naught, used by Atkins is 1 bar. So P naught is equal to 1 bar, and that's 10 to the 5th pascals. And note that 1 atmosphere is 101,326 pascals, which is 760 torr, or 760 millimeters mercury, and all of these are exact. So note that 1 bar is not exactly 1 atmosphere. Because it's 10 to the 5th, we're losing this 1326 there. Also, note that while Atkins uses the notation P naught like this with a line through the 0 to denote the standard state, I'm generally going to use P0 to talk about P naught for simplicity. It's going to be up to you then to translate between my notation here and Atkins' notation that he uses there. Furthermore, in nearly all cases in which Atkins refers to a perfect gas, I'm going to call it an ideal gas instead. And there is a difference between an ideal gas and a perfect gas. This is explained further in Chapter 5. An ideal gas is a gas in which the interactions between molecules in a mixture are all the same. And a perfect gas is an ideal gas in which those interactions are 0. But again, I'm going to use the terms ideal gas and perfect gas interchangeably unless I wish to stress the difference between an ideal gas and a perfect gas, which again is really only going to come about in Chapter 5. So normally I'm going to call it an ideal gas, whereas Atkins calls it a perfect gas. And it will once again fall to you to realize that in most cases, the term perfect gas is actually a more descriptive term and more applicable to what I'm talking about, but I'm going to use the term ideal gas because it's far more commonly used than the term perfect gas is. So you should bear in mind the difference between the two. You should realize that when I say ideal gas, most of the time I really mean a perfect gas. So if two gases are separated by a movable wall, in other words, a piston, so we've got some gas over here, some other gas over there, the gas that has the higher pressure will tend to compress the gas with the lower pressure. So if we have high pressure here and low pressure there, the piston will tend to move to the right. If, on the other hand, we have the high pressure on the right, low pressure on the left, then the piston will tend to move towards the left. Until, of course, those pressures become equal, and now there's no net tendency for that piston to move one way or the other. Now, the reason why the piston is moving is because that piston has a greater force applied to it from one side than it does from the other. So if there's low pressure, we have some number of collisions on there, but on the other side, we either have collisions that are striking with more force, or we have more collisions coming from that side, from the higher pressure side. So we know that that piston will move as long as it is able to move. And so when those two pressures are equal, then the piston no longer moves, and now we've reached a state of equilibrium. In this case, we've reached a state of mechanical equilibrium, an equilibrium between one side and the other. Now, we measure pressure with what's called a barometer. The original design by Torricelli, who was a student of Galileo, was an inverted tube of mercury that was sealed at the top with a vacuum up there. And the air pressure outside pushing on the mercury in the pool here was enough to lift that mercury up some distance into that glass tube, up towards that vacuum. So if there's a vacuum in there, then there's nothing pushing down on the mercury aside from gravity pulling down on the mercury inside. But because there's air outside, then basically we have the weight of that column of mercury inside is equal to the weight of air pushing down on the outside. So that air is going to go up all the way up to the top of the atmosphere, all the way up to space. And so if we can get that column of mercury, 760 millimeters of mercury, are going to be suspended on an average day at sea level by the weight of air pressing down on the outside of that tube. Now, a more advanced, meaning somewhat safer, barometer has the shape of a J or a U, where one end is sealed off here and we still have a vacuum up there, and at the other end it's now open to atmospheric pressure. And this is safer because now all of our mercury is contained in the tube. It's still not perfectly safe because, number one, we could break the tube and let the mercury out. Mercury is, of course, very toxic. Or we could get some of the mercury vapor to come out this open end of the tube. Now, modern barometers are generally electronic, and they've generally moved away from using mercury because of the safety hazard presented by mercury. So now let's define temperature. You probably know what the temperature of some object is. You have some sense of it. But in physical chemistry, we're going to define this very carefully. We're going to define the temperature T as the property that indicates the direction of the flow of energy through a thermally conducting rigid wall. Now, if energy flows from A to B when in thermal contact, then we can say that A has a higher temperature than B does. If, on the other hand, energy is flowing from B to A, then B has a higher temperature. If there is no net energy transfer from A to B or vice versa, then we can say that those two systems are at thermal equilibrium. They are at the same temperature. So we have two different types of boundaries. A diathermic boundary is a boundary that is thermally conductive. It's going to allow heat to flow, or it's going to allow energy to flow through that barrier as heat. We also have adiabatic boundaries. So this is a boundary that is thermally insulating. We're not allowing any energy to flow through that barrier as heat. And note that while some barriers, like the walls of a vacuum flask, this is a Dewar, have very low thermal conductivities, there are no truly adiabatic barriers in existence. Just like there are no truly ideal gases. So there are no truly adiabatic barriers because no barrier can prevent black body radiation from being transmitted through itself or emitted by itself. So thermal equilibrium is the state in which two objects in contact, perhaps through a diathermic barrier, have no net energy exchange. That is, if two objects are at thermal equilibrium, then we can say they're at the same temperature. So this brings us to the zeroth law of thermodynamics. If A is in thermal equilibrium with B, and B is in thermal equilibrium with C, then C is also in thermal equilibrium with A. Now we can show that down here visually. A is in thermal equilibrium with B, B is in thermal equilibrium with C, and that means that C must be in thermal equilibrium with A. So the zeroth law allows us to use a thermometer to measure and compare the temperatures of objects not directly in thermal contact with one another. So B could be our thermometer. We can put it in thermal contact with A, and we read some value. If we then put B into thermal contact with C, and it reads that same value, then we know that C must be at the same temperature as A. And this now brings us to the thermodynamic temperature scale, which is simply the Kelvin temperature scale. Now we're going to get into further detail about the Kelvin scale later on in the course. And that was the states of gases.